It is closing time at a restaurant, and the owner is doing the thing owners do at closing time, which is arguing with a page of numbers. She knows 240 people ate here tonight. That number she is sure of, because every one of them paid. What she has lost track of is how those 240 people were sitting. Now, there is a second number she happens to know, and it is a stranger one. If you had stopped every single diner on their way out and asked them, how many people were at your table, and then averaged all 240 of those answers, you would have got 4/3. Notice that this is not the average table size. It is the average table size as experienced by a person sitting at one, which is a different and slightly larger thing, because the big tables get to answer more times than the small ones do. So she has two numbers, 240 diners and an experienced average of 4/3. And the question I want to ask you is this one. From those two numbers alone, how many people ate here alone tonight? The tempting answer is that you cannot possibly know, and that she would have to reopen the book and read the seating chart line by line. Hold on to that instinct, because it is exactly the instinct this whole story is about. She does not need the book. Those two numbers are enough to prove that at least 160 people dined alone. And I want to show you why, because in about 15 minutes, that same argument is going to tell us something about the zeros of the Riemann zeta function. Here is the only fact we need, and it is a fact about whole numbers. Take any table with some number of people at it. Call that number m. Then, m squared is at least 2m minus 1. Why? Well, m squared minus 2m plus 1 is m minus 1, all squared. And a square is never negative. And the thing worth noticing is when that inequality is tight. It's an equality exactly when m is 1. Every table of 1 gives you nothing away, and every table of 2 or more leaks. So now add that up over all the tables, and watch where that minus 1 actually gets paid. A table of 2 or more already clears twice m with nothing taken off, since m squared minus 2m is m times m minus 2. Only a table of 1 costs you anything. So the sum of m squared is at least twice the sum of m minus the number of tables that held exactly one person. The sum of m is just the number of diners, 240. The sum of m squared is 240 times that experienced average of 4/3, which is 320. Rearrange, and the number of tables of 1 is at least 480 minus 320. 160. And a table of 1 is one person, so that is a count of people, not of furniture. 2/3 of the room, eating alone. Proved from two averages, and we never once looked at where anybody was sitting. So where does a restaurant get us? Here is the strip, and the line down the middle of it at real part 1/2. Riemann's guess, which nobody has proved in 166 years, is that every one of these zeros sits on that line. We're going to work in a window between height t and height 2t, and we're going to count what is in it. And we need to be careful about counting, because there are 4 different counts, and this whole subject turns on telling them apart. N is every zero in the window, counted with multiplicity, so a double zero counts twice. N naught is the ones on the line. N naught star is the ones on the line counted as distinct points, so a double zero on the line counts once. And N simple naught is the ones that are both simple and on the line. The theorem we are heading for is a statement about the third of those, measured against the first. The reason any of this is reachable is the explicit formula. It says that a sum over the zeros equals a sum over the prime powers plus some Archimedean junk from the gamma factor. It is a balance. Push on the primes and you learn about the zeros. And that is the only bridge we have. In 1973, Montgomery did exactly the restaurant argument to the zeros. The tables become the distinct zeros. The number of people at a table becomes the multiplicity of that zero. And the experienced average, the strange second number, becomes a second moment over pairs of zeros, which he evaluated by pushing it across the explicit formula onto the primes. What he got was that the sum of m rho squared is at most 4/3 of n, the same 4/3. In the same integer fact, m squared at least 2m minus 1 then says that at least 2/3 of the zeros are simple. If you want distinct zeros instead, you can push it to 5/6 using m squared at least 3m minus 2, which is the same trick one notch up. And there is a price. To evaluate that second moment on the zero side, Montgomery needed the ordinates of the zeros to be real numbers, because the argument reads that sum as a sum of positive squares and picks the diagonal out by sign. The ordinates are real exactly when the zeros are on the line. So the proof that 2/3 of the zeros are on the line assumed that all of them were. Hang on. If you assume the Riemann hypothesis to prove things about the zeros, haven't you just gone in a circle? That is the right thing to be suspicious of, and the answer is that only half the argument leaned on it. The prime side is a mean value of a Dirichlet polynomial of length t. It never needed the hypothesis, and it never did. It was only the zero side, only the step that wanted those ordinates real, that was borrowing. The other road starts with Selberg in 1942, who got some positive proportion without saying what it was. Then Levinson in 1974 found a completely different method, mollifying zeta near the line, and got a third. Heath-Brown noticed those zeros were simple. Conrey pushed it past 2/5 in 89. Bowie, Conrey, and Young, then Feng, then Pratt, Robles, Zaharescu, and Zeindler ground it up to 5/12, which is 41.66%. And there it sat, from 2020 until this year. Every result on that road used Levinson's method, and Levinson's method had run out of room. Now look where Montgomery's 2/3 is sitting. Up there, unreachable, with a hypothesis attached to it. Two things happened recently that matter. Balliot, Goldston-Suriajaya, and Turnage-Butterbaugh made it fully explicit that Montgomery's prime side evaluation holds for the sum over all complex zeros, hypothesis or no hypothesis. That green pan was always free, and now it was written down as free. Then Goldston and Suriajaya went and isolated exactly what was left. They showed Montgomery's 2/3 follows unconditionally if you assume every zero sits within a hair of the line. And then they asked, in print, what would follow if the Riemann hypothesis could be removed from Montgomery's proof? So the wall had been reduced to one word. Everything in that argument was unconditional, except the step that wanted a sum of positive squares. Positivity. What if we stop asking for it? Take Weil's form, feed it two test functions, and it gives you the sum over all the zeros of f hat at gamma rho times g hat at gamma rho, weighted by multiplicity. That form being positive on every compactly supported test function is not merely related to the Riemann hypothesis. It is equivalent to it. So asking for positivity on the whole space is asking for the whole conjecture, and we are not going to get it. But we do not have to test the whole space. Restrict the form to a finite family of test functions, and all you have left is a finite symmetric matrix. I like to picture it as sampling. Take one fixed, compactly supported window, make about lambda n modulated copies of it with center frequencies spread evenly across the window from t to 2t at exactly the critical density, and let G be the matrix of the form on that family. In time frequency language, that family is a Gabor system at critical density, and G is its Gram matrix. In operator language, G is a finite compression of the operator, whose full positivity is the hypothesis. Either way, the point is the same. We have traded an infinite dimensional statement we cannot prove for a finite square of numbers. And a finite matrix is a thing you can take apart. Now, split the matrix by where the zeros are. Write G as P plus Q, where P collects the contributions of the zeros on the line, and Q collects the rest. A zero on the line has a real ordinate, so its sampling vector is a real vector, and its contribution is that vector times its own transpose. A rank 1 non-negative block. Stack up all the online zeros, and P is positive semi-definite with rank at most the number of distinct points on the line. Off the line, the functional equation does the work for us. It forces the zeros into mirrored pairs, rho and 1 minus rho bar, sitting either side of the line. Their ordinates are complex conjugates of each other, so their sampling vectors are complex conjugates too. And the pair contributes V times V transpose plus V bar times V bar transpose. That block has signature 1, 1. One positive direction and one negative direction, which is a hyperbolic plane. Couldn't the offline ones just hide? Make the negative parts cancel something and slip out of the count? They cannot, and Sylvester's law of inertia is why. Pulling a form back along a map never increases its positive index, so Q has at most one positive eigenvalue per offline pair, which means an offline pair buys exactly one positive direction, and it costs 2 zeros out of n to buy it. Every zero that runs off the line pays double for the privilege, and that asymmetry is what the rest of the argument lives on. So what do a trace and the norm actually buy? The first thing anyone would try is Cauchy-Schwarz, and it is worth watching it work because where it stops is what forced everything that follows. The trace of a Hermitian matrix is at most the sum of its positive eigenvalues, and Cauchy-Schwarz says that sum is at most the square root of how many there are times the Frobenius norm. Rearrange, and the number of positive eigenvalues is at least the trace squared over the norm squared. Feed in the two moments at lambda 1, and that is 3/4 of n positive directions. Now do the bookkeeping. Write S for the online points and P for the offline pairs. Every one of those positive directions was bought by one or the other, so S plus P is at least 3/4 n. But n counts every zero with multiplicity, so n is also at least S plus 2P. Subtract the second from twice the first, and S is at least twice 3/4 minus 1. 1/2. 1/2 of the zeros on the critical line, unconditionally, which already beat 5/12. So you go looking for a better window, and optimizing it moves 1/2 to 0.5066, and then it stops. So the bottleneck was never the window at all. It was Cauchy-Schwarz itself. Here is the inequality that fixes it. Let P be Hermitian and positive semidefinite with rank at most R, and let Q be Hermitian with at most B positive eigenvalues. Then R is at least 2 trace P plus 4 trace Q minus 4B minus the Frobenius norm of P plus Q squared. Notice what's different. Cauchy-Schwarz only ever saw a count of positive eigenvalues. This sees the rank. The proof is 3 squares, and you've already seen the first one. You can reduce to the case where P and Q are simultaneously diagonal, because at a minimum of the relevant functional, the two commute. So let AI be the eigenvalues of P, which are non-negative and vanish past R. Let BI be the eigenvalues of Q, and let XI be their sum. Then, the Frobenius norm squared is just the sum of the XI squared. And we want to bound each XI squared from below by 2AI plus 4BI minus as little as possible. Case 1. If I is at most R and BI is not positive, use x minus 1 all squared is at least 0. That gives x squared at least 2x minus 1, and since minus 2BI is already non-negative, we pay 1. Case 2. If I is past R and BI is not positive, then AI is 0. And x squared at least 0 does the job, with minus 4BI to spare, so we pay nothing at all. Case 3. If BI is positive, use x minus 2 all squared. That gives x squared at least 4x minus 4, and 2AI is non-negative, so we pay 4. So what does all of that cost us? Add it up. The total we pay is at most R, 1 for each of the first R, plus 4 for each positive eigenvalue of Q. Rearrange and the lemma falls out. And look at what case 1 actually was. It was m squared at least 2m minus 1, the restaurant, wearing a matrix. I've been quoting those two moments without paying for them, so let me show you where they come from, because this is the one part of the argument that is genuinely hard analysis rather than bookkeeping. Both the trace and the Frobenius norm are integrals of an explicit kernel against the density that the explicit formula hands you, and that density has 3 pieces. One Archimedean piece built from the gamma factor's logarithmic derivative. One prime piece, a sum over prime powers up to x of von Mangelt's lambda of n over root n times cosine of tau log n. And one piece coming from the pole of zeta, which is small enough to throw away. The trace is the easy one. For the norm, you have to square that density and cross-multiply, and most of the cross terms cancel because the cosine in the prime piece oscillates and the window integrates it away. 2 survive. The Archimedean square is the term that gives you the 1 over lambda, and the prime piece squared splits, the way every second moment in the subject splits, into a diagonal, where n equals m, and an off-diagonal, where it does not. The diagonal is where lambda over 3 is born. Integrating cosine squared of tau log n across the window gives you a clean t over 2. So, you are left with a sum of lambda of n squared over n against a smooth weight. Jebyshev and Mertens tell you that sum up to t is a half log squared t, and partial summation turns it into an integral of y against the window's self-convolution. Do that integral, and out comes lambda over 3. The off-diagonal is the half that could have killed the whole thing. It is a bilinear form in x n equals lambda of n over root n, with denominators log n minus log m. And that is exactly the shape Montgomery and Vaughan's generalized Hilbert inequality was built for. The frequencies log n are spaced by at least 1 over n plus 1, so the entire off-diagonal is bounded by t log squared t, which is a full logarithm below the main term. It dies, and no sieve constant enters anywhere. And now you can see why lambda is not allowed past 1. Push x beyond t, and the off-diagonal stops being dominated by the diagonal, and controlling it would mean knowing about pairs of primes at Hardy Littlewood strength. Nobody can do that. That is the wall this whole method is standing next to, and in a few minutes, it is going to set the ceiling. Now put it together. The prime side says the trace of g is n, and the Frobenius norm squared is 1 over lambda plus lambda over 3 times n. Feed those into the lemma with p the online part and q the rest. Use that the trace of p plus twice the number of offline pairs is at most n, and you get 4n minus 2n minus 1 over lambda plus lambda over 3 times n. At lambda equal to 1, that is 4 minus 2 minus 4/3. 2/3. At least 2/3 of the zeros of the zeta function in every high enough dyadic window are distinct points sitting on the critical line, and nothing anywhere in that argument assumed the Riemann hypothesis, which answers the question I left you with at the restaurant. How do you count a thing you can't look at? You refuse to look at it one at a time. 2 moments and 1 fact about integers, except the fact about integers had to grow up into a fact about eigenvalues first. So what else does that one lemma buy? 2 more theorems, for almost nothing. Run it again, but this time put only the simple online zeros on the rank side and move the multiple online points across to the index side, where they sit alongside the offline pairs at a flat charge of 4. The inequality now reads 3s1 plus 4s2 plus 4p is at least 4 trace minus the norm. That is the matrix version of m squared at least 3m minus 2, the second level of integrality. And the arithmetic comes out the same. 2/3 again, except this time it says 2/3 of the zeros are simple and on the line, which is strictly stronger than what we'd got. And if all you want is distinct zeros, each point counted once, whatever its multiplicity, the same run gives 1 plus 2/3 over 2, 5/6. The record for that was 0.6603. So one lemma, applied 3 ways, moves 3 separate records at once. One last refinement. You can still choose the window, and if you optimize it properly, you land on cosine of root 2x on the interval from -1/2 to 1/2, which is exactly the kernel Montgomery and Taylor wrote down in 1975. It is the function whose second derivative plus twice itself vanishes, and that is what makes a certain integral come out constant across the interval. The constant is 3/2 minus 1 over root 2 times cotangent of 1 over root 2. 67.25% and 83.6% for the distinct ones. So is the hypothesis in trouble? No, and the paper says so itself before anyone else can. The argument gives lower bounds and nothing else. That remaining third is not shown to be off the line. It is gray because the certificate never reaches it. And the method knows its own ceiling. The inputs here are satisfied by objects whose analog of the hypothesis is false, like the Davenport-Heilbronn function. So nothing in this argument could ever separate 2/3 from all. Given only the trace, the Frobenius norm, and the block structure, the inequalities are sharp, and no certificate reading bandwidth 1 data can certify more than about 68.2% of simple zeros. Which means 2/3 is within 1.5 points of the ceiling of its own method. Getting to 70 or 80 or 90% this way would need pair correlation out to bandwidth 1.04, 1.26, and 1.7. And none of those are things anybody currently knows how to get. One more thing, which is, who wrote this? The paper's author line says Claude. It was written by a model at Anthropic that had been asked to take a real stab at the Riemann hypothesis, and it failed at that, and this fell out sideways on the way. About 60 copies of it worked in parallel for a day and a half, and the first certificate they got was 1/2. You have seen exactly why it was 1/2, and exactly what had to be found to move it. It has a lean formalization, and 2 mathematicians at Anthropic have gone through it, and Conrey and Goldston looked at it on short notice. It has not been refereed. The model's own last word on it was that it needed a human analytic number theorist. So nobody can find these zeros. But if you know two averages about them, and you know that a square is never negative, you can prove that most of them are exactly where Riemann said they would be.